In this video, we will be building on what we did last time when we were investigating negative feedback, and we will actually look at how negative feedback can lead to oscillatory behavior. So again, we will start off with the Goodwin model that we used last time, and we will use a modification by Griffith to simulate these oscillations. So very similarly to last time, we have the differential equations that I've highlighted now, and these differential equations specify our model, and they look very similar to what we did last time, with one small difference, and the difference is that in this term here, this inhibitory term in the first equation, we have an exponent n. And so what we want to look at in this video is how n can lead and how changing n can lead to oscillatory behavior. So we've kept the model definition and the simulations from last time, from the last video. So these are identical to what we wrote up then. And all we need to do now is implement that modification with the exponent n. So how do we do that? The exponent n turns up only in the first equation of the model, and it's the exponent of x3. So let's go ahead and go into the Goodwin model definition here at the bottom, and just simply add in that exponent n. So now we are done with that. Then we of course will need to add in an extra parameter that we will be changing in the model. So we want to add here in this line of parameters that n is equal to the fourth element. Okay, so we're done with the model now, and we just need to implement that in the simulations as well, and all we need to do there is to put in some value of n, and we will start off now with n equals 1, and then we just have to append it in the list of parameters, and that's it. So now we want to see what this looks like. So let's run it. And we get this figure that looks identical to one of the figures we did in the last video. So again, we have this negative feedback system, and here it's identical because we've left n to equal to 1. What happens though if you increase the value of n? Let's try what happens. So let's put n is equal to 5. And let's run it again, and I've plotted it on top of the previous figure to show that now we have much more of these oscillations here. So instead of just having a peak and then it's sort of steadily going into this steady state, you have a lot more of these peaks and troughs. But now the question is that, okay, do these oscillations eventually die down, or will they continue oscillating? And what we can do here is we can increase the time range to investigate what happens. So let's have a look at what happens. For example, when we set the maximum time to 100. So let's replot that. And as you can see now, it's obvious that towards this long time period, the oscillations do die down. Nonetheless, you have a few oscillations happen, so it's not the critically damped system that we had with n equals 1. And you can have a look at our video on the inhibition function that will tell you a little bit more about the shape of that function and how n will influence that behavior. Okay, but we still don't get steady simulations in this system. So what happens if we increase n again? Let's set n to 10 this time, what happens? So let's replot it. And now, as you can see, you actually have these oscillations continuing on to n equals 100 with a very, very high amplitude. So in this particular case of n, it won't actually ever die down as in the previous examples. You are encouraged now to have a look, have a play around with values of n, and in fact try to find a critical value of n where you will observe oscillations and where you don't. This is the end of our video. Thank you for watching.